Alright, our next lesson is going to involve an operation of functions that are making new functions from functions that we know already. You've seen composition of functions, I think, in Algebra 2. That's just one of the ways we can construct new functions from some that we already know. We can construct new functions from simply adding two given functions that we know. Here's f of x is x squared, g of x is the square root of x plus 1. We get a new function, f plus g of x, if we add f and g. We would end up with x squared plus the square root of x plus 1. What would the domain of this new function be? Well, because g of x has the restriction that, let's see, what is the domain for g of x? We'd say x plus 1 has to be greater than or equal to 0. X has to be greater than or equal to negative 1. So the domain is, in interval notation, bracket, negative 1, all the way to positive infinity. It's the restriction on g. Well, that would also be the domain for the f plus g of x. How about f minus g of x? Well, it's the same thing. X squared, except this time we subtract g of x, square root of x plus 1. And the domain is the same, from negative 1 to positive infinity. How about f times g of x? F times g of x would be x squared times the square root of x plus 1. And it would also have the same restriction on the domain as the first two, from negative 1 to positive infinity, inclusive. And then how about f divided by g? That would be x squared divided by the square root of x plus 1. Now, what is the domain of this resulting function? Well, if we include negative 1, like we did for these others, remember the domain for all of these others was negative 1 to positive infinity. If we include this as the domain for f divided by g, our new function here, then 0, the negative 1 in the domain would result in a 0 denominator, undefined. So the domain for this function is not what we've been using. It would have to exclude the negative 1. We're always going to be on our toes for domain. And here's an interesting twist. What do we get if we multiply g times g of x? We would get, if this is g of x right here, we would get the square root of x plus 1 times itself, which would be squared. And if I square the square root, I just get the x plus 1. Does that change the domain? Let's see, I could take any real number and add 1 to it. Does this make, question mark, the domain become any real number? And the answer to that question is no. Okay, no. The domain of g still has to be respected. So the domain of, if it's not in g, then we can't, and then it won't be in g times g of x. So the domain then is still of this resulting function, negative 1 to positive. Let's take a look at those two functions again. F is x squared and g is the square root of x plus 1. And let's just recall that if I wanted to find f of 3, or f of something, we plug 3 in for x. F of 3 would be 3 squared, or 9. Or let's find g of 8. That would be the square root of 8 plus 1, which is the square root of 9, which is 3, coincidentally. We just plug something in for x. That's what we're going to do with the composition of functions. The composition of functions is just plugging in one function for x in another one. F composed with g, the way it's written here, is indicative that we're just going to take all of g of x and plug it in for x, just like we did finding f of 3. However, you'll see it written this way more frequently. This little circle, this little thing looks like a multiplication dot that is left open. That's called f composed with g. That's how you read that. F composed with g. Abbreviated, maybe you'll call it FOG, but it means F composed with G. And let's see what that is in this particular case. F composed with G. So we're going to take G and plug it in for X. F squares something. We see here that the function f of x is just taking something and squaring it. F composed with G would be F composed with g of x would be take all of g and square it. It would be the square root of x plus 1 quantity squared, which again is x plus 1 simplified. Now, what is the domain of f composed with g? The domain is not all real numbers, just like when we did g times g in the last example. Since g has a restriction on the domain, so does f composed with g. So does this new function right here. Okay? Its domain would be just like it was with g times g. It would be from -1 to positive infinity. Let's have a quick practice. I'll do number 1 with you. F composed with g of x. Given that f of x is 2x plus 3, and g of x is the sine of x. Okay, we're going to plug in sine of x right here. F of the sine of x. And what does x do? F takes something, multiplies it by 2, then adds 3. In this case, it's going to be the sine of x. So it's going to be 2 times the sine of x, and then add 3. F composed with g of x is 2 sine of x plus 3. All right, you complete the 2 steps on number 2. Well, for g composed with f, we'll just take f and plug it in for whatever we're taking the sine of. Okay, so it's going to be g of 2x plus 3. And g, you see, is taking the sine of something. So the function would be take the sine of 2x plus 3. All right, let's kick it up a notch. We want to do f composed with g composed with h. And they're all defined right here. So our first step would be, actually working from the right to the left. First, we got to find out g finds the sine of something, and in this case, of h of x. So we got to plug in h of x here, x squared plus 1. So that would be the sine of x squared plus 1. F of the sine x squared plus 1. And f multiplies times 2, something times 2, and then adds 3. And this is what is going to multiply times 2, and then add 3. It's 2 times the sine of x squared plus 1 plus 3, or 2 the sine of x squared plus 1 plus 3. And it's fair to ask, what's the domain of this function? And since we can square any number, we could take the sine of any number. There should be no restrictions on the composed function unless there was a restriction on any of the individual functions. And since any number can be squared, and we can take the sine of any number, and we can multiply any number times 2, there was no restrictions on the domain. The domain is -infinity to positive infinity. let's do it with some numbers. Okay, let's find f composed with g of 2. First find g of 2. 2 plus 1 is 3. And then find f of 3. F squares a number. 3 squared equals 9. That was easy. Let's try g of f of 2. The f of 2 would be 2 squared is 4, and g of 4 would be 4 plus 1 equals 5. Hey, that's simple. About f composed with g of x. F squares something. What's it going to square? X plus 1. Okay. Which would be x squared plus 2x plus 1. How about g composed with f of x? Okay, g takes something and adds 1. What's it going to take? F, x squared, and then add 1. And that's it. Now we want to take it maybe backwards. If h of x is the composition of two functions, what might those two functions be? Okay, what would f be and what would g be in order to compose them and end up with this? Well, it's not unique. There may be multiple things you could say. But we could say maybe g of x could be 1 plus x cubed, and f of x is x to the 27th power. So that f composed with g of x, we're just taking g and plugging it in for x in the f of x expression. We would end up with 1 plus x cubed, and then raise that to the 27th power. Okay. I would like to see you do the next one. See if you can come up with an f and a g that, when composed, would end up with this. Now, this is one example of a solution. F of x is the exponential base e raised to the x power, and g of x would be negative x squared, the opposite of x squared. So we're just taking this and plugging it in right there and get k of x, get the composition. All right. Take another effort and find a composition that gets L of x. And maybe you came up with this expression for f and g. Maybe you came up with something else that works, because this is not unique. You can ask me about your solutions tomorrow. I want to turn our attention now to a graphical approach to this composition idea. Let me change the screen. Okay, take a look at what we've got set up right here, just graphically. Disregard the over here on the right, the numbered part. We've got two graphs. One is a solid black line. Can you see it running this way? Okay. And then the other one is the dashed line. The dashed one is g of x, and you can see here that the solid one is f of x. Okay. Knowing that, can you find a value for f composed with g of 5? F composed with g of 5. Well, if you remember what composition means, what you're looking for first is g of 5. G of 5, let's see, when x is 5, look over here, and then x is 5, the value of g at x equals 5 is 0. So g of 5 is 0. Now we need to plug that into f. What is f of 0? Well, when x is 0, f is 0. So f composed with g of 5. F composed with g of 5 is 0. Let's try g composed with f of 5. So first we find f of 5. F is the solid black one. Come out here to 5, x equals 5. We got to go all the way up here. And it's almost not even on the graph. Well, it's not. We estimate that to be, let's say, 5. F of 5 will be 5. And then we find g of 5. G of 5 is right here on the dashed line. When x is 5, g is 0. Let f composed with g of 0. Okay. F composed with g of 0. Well, g of 0, when x is 0, the value of g is 1, and f of 1 is right up here at 1. Okay. Let's try f composed with f of 5. Well, f composed with f of 5. F of 5 we found earlier when x is 5. F was way up there at 5. And then f of 5 again is 5. Okay, here's a new set, 5, 6, 7, and 8. Let's see if you can find number 5. G composed with G of 5. Graphically, G composed with G of 5. First we find G of 5. Here it is. When x is 5, G is 0. And then find G of 0. G of 0 is 1. So we say 1. Do number 6. G composed with G of negative 3. First find G of negative 3. Let's see. It's 0. And then find G of 0. It's again positive 1. Try G composed with G of negative 1. Well, G of negative 1 would be right there, a value of 0. And G of 0, wow, again, 1. Well, first we have to find f composed with G of 1. First find G of 1, which looks to be 2, right at this local maximum. And then f of 2, well, let's see. F of 2 would be right here at 0. So f composed with G of 1 is equal to 0. And here's a new set. We don't have to do all of these, but maybe we'll pick off one of these 3-stage ones, these 3 compositions. Let's do number 10. F composed with G of 4. First find G of 4. Let's see, at x is 4, G is negative 1. F of negative 1 would be 0, and then f of 0 would be positive 1. So number 10 here is positive 1. And so that's it for today. We'll see you tomorrow for the exercises.